Okay. Hello, everyone. My name is Ajay Jacob. I am the Director of Projects at the California Dreams Hub. It's my pleasure to invite Dr. Hamid Shojai. He is a distinguished engineer at Cadence. He leads the AI initiatives transforming chip design and verification. He is the co-founder and former CTO of ChipStack, which was acquired by Cadence. Uh, in ChipStack, he led the development of autonomous design and verification systems powered by large language models. Hamid received his PhD in computer engineering from University of Wisconsin-Madison. He previously contributed to multiple generations of TPU accelerators at Google. He also worked at Light Matter, where he held technical leadership positions, managing the verification for cutting-edge photonic AI hardware. He has also worked at Qualcomm on advanced SoC verification and methodology. And his work focuses on advancing the transition from traditional chip design flows to autonomous AI native hardware development. Today, Hamid is going to give us a talk on AI-driven hardware verification from automation to autonomy. Thank you, Hamid, and the stage is yours.
Thank you very much, Ajay. Hi, everyone, and thank you for having me. So today I want to talk about what it actually takes to build AI systems that can do hardware verification. So it's not just assisting with it, but just reasoning through it end to end. The framing I'm using here, like from automation to autonomy, is intentional. Automation is EDA has been around for decades. We have been doing scripting, we had linters, formal property checkers, regression runners, and so on. What I'm going to talk about today is a different category. This is systems that can read the design, understand the design, they can build an understanding of the intent, they can decide what needs to be tested against the design, they can generate the test infrastructure, they can run it with EDA tools, and close the tool. So that's a completely different engineering problem. And most of what I will share today is about what makes it hard and what we have learned solving this problem. So here's our roadmap for today. So we'll start with the problem, why chip verification is such a brutal bottleneck. Then we look at the product, what ChipStack actually does and how it is structured. We'll go deeper into architecture and the Symfony framework. Then I'll spend a good amount of time on models and fine-tuning both SFT and RFT experiences because that's where a lot of interesting engineering happened. We'll cover evaluation and KPIs because if you can't measure it, you cannot improve it. And finally, we'll close with the constraints, learnings, and where this is all heading. So let me start with this context. So we are living in a special moment in compute demand. Both Sam and Demis have been explicit. We need more chips than ever before, and chips and AI research are in a tight feedback loop driving towards AGI. But here is the problem. It takes more than 2 years and hundreds of engineers to design and verify a modern chip. And that timeline is getting longer and longer, so not shorter, because the designs are getting more and more complex. So the chip supply chain is a bottleneck for AI progress. So AI progress is blocked by the number of chips that we can deliver. And within that supply chain, verification is the biggest bottleneck of all. Let me make that concrete with some numbers. So verification effort has increased 5x over the last decade. When you look at how engineering time is actually spent in a chip design project, in my experience, over 60% of the schedule is consumed by verification function. Usually, like 3 out of 5 headcount on the chip team are verification engineers. Even designers, they have to do also verification at some point and help with the debugging and root causing the issues. 76% there is risk for costly respin if bugs are skipped from verification, and the cost for a respin is over like 30 million. So this is what I call a hair on fire problem. It's not a nice to have optimization. It's the rate limiting step in building new silicon, and it is very manual today. So we have to do something to improve it. So what's the solution? The answer, what we build is AI-powered chip verification engineers. So we don't do copilots. We don't do like autocomplete. We have developed agents that can do the job end to end. And let me show you what that looks like. This slide shows the core stack flow. You give it a design and a spec, then agent can understand the design. It will read all the design inputs like RTL, specs, block diagram, whatever artifacts you have related to design. You can read them and understand what is this design. It can figure out what to test and can build a mental model out of the design. And from there, it can generate a test plan to show you what needs to be verified with respect to this design. After test plan generation, the tool can write test code. It could be like assertions for formal verification or UVM code for simulation. It can also develop coverage models. We have integrated EDA tools in the flow. So our agents can run Jasper for formal verification. They can run Excellium for simulation and validate the results before we give it to the user. And our agent is end-to-end. So that means that they can run the test bench, they can read the results, they can fix and debug, and ultimately they will close the loop. Another important consideration here is that the user stays in the loop in a pilot mode. So you can guide and redirect the tool, but the agent is doing the heavy lifting. So basically, what we are saying here is that LLM cannot replace DB engineers. DB engineers should be still in the driving seat and drive the tools to the end. So in summary, you can go from design to 80% functional coverage in minutes for tasks that used to take like more than a few weeks. Beyond the core flow, ChipStack is built to fit into how real team works today. We are relying on four key principles. So we have provided a modern UI UX. This is a new interface for human agent collaboration that makes it feel like you're working with a very capable teammate, not a command line tool. So it's a new interface that user can use to review the results that are given by the tool, give feedback and update them until they're happy with the results. We have deep integrations. So our solution works with your existing EDA tools and verification infrastructure. We don't give like rip and replace solution. So it just works with your flow. Privacy is very important for us. So our solution, you can deploy it fully on-prem, which is also very critical for semiconductor companies because they usually have confidential IPs that they are not willing to share. Our solution supports both formal verification and simulation-based approaches, which is also another important aspect because different blocks need different methodologies to be verified. So I want to pause here and make you feel the pain before I show you the solution. So these images in this slide represent what traditional verification looks like. We usually have many scripts that we write to run verification. We have manual test management. There is endless regression cycles, and we usually have like human-driven debugging, which takes a lot of time. Engineers spend like 60% of their time reading the log files and chasing tool errors and like debugging the waveforms until they can get to the root cause and the issue that was causing the failure. This is the status quo. It's as you can imagine, it's not sustainable at the scale that today industry needs. And now, what if it was this? Like, what if you can go and just write a very high level, give an instruction to the tool, say, for example, verify this feature in my design, very high level instruction. The tool can take it and go and generate a test plan for you. The user can review the test plan. If they like it, they say, okay, go ahead and generate code for this test plan. Our tool will generate code, will do syntax checking, will make sure the tool can run, the code can run. You can review and give more feedback if you don't like the code. So again, this is high-level feedback. Tool will update it, will show you what is updated. If you like it, you can accept that and submit the code. And when you're happy with the code, you can say, okay, just go ahead and run the test. So we will figure out how to run the test. You don't need to write TCL and setups. It will run the tool and show you the results. If the test is failing, for example, in this case, it will give you a hint why we feel the test is failing. The user can review that. If that makes sense to you, then you say, yeah, this is good. So go ahead and apply it and fix the issue. The tool will fix it and run again and show you the final results. We can even do debugging on the framework itself. So we have waveform viewers. You can bring the waveform, look at the signals, and give instructions until you figure out if the hint is correct or not. And as I said, you can be on the driving seat. You instruct the tool until like everything is passing, and at the end you can dump all the artifacts and go to the next step. So you see, this is like future. So you just give high-level instruction, and the tool can do the heavy lifting part. Let me introduce the 4 production agents in the ChipStack platform. So the first one is what we call mental model agent, and that extracts the design intent, like functionality of the design, interfaces, protocols, hierarchy. So this is the foundation that every other agent builds on. We also have a formal verification agent that can deploy like property-based formal verification at the scale. This is targeted for formal verification engineers who want to go faster without writing like every assertion by hand. We have another agent, which we call it unit testing agent. This agent enables like test-driven development for designers. Designers can use this agent to catch bug at the RTL stage before they become verification problems downstream. We also have a UVM verification agent that can handle the full simulation-based flow. This agent can generate test plan. It can also develop testbench. It can also do coverage closure and even debug your regression and root causing and help you to fix the issues. The key insight here is that all of these 4 agents need context, memory, and reasoning. And that's exactly what modern LLM-based agents are good at. And that's why we hope that we can solve this problem, which is a reasoning problem, but by AI agentic solutions. Now let's go under the hood. I want to walk you through the architecture that we have developed and how that architecture works. As I said, the ChipStack AI super agent allows engineer to interact with verification workflow using natural language. So our super agent takes that natural language. For example, you can say, verify this design using simulation. What it does is that first, it takes all the design inputs like RTL, spec, block diagrams that you have, and it will build what we call a mental model of the design, which is a structured representation of the design. And I will provide more details on that. Using that mental model, it can go ahead and generate all the necessary verification collaterals. And it can even run verification workflows. If it is like formal verification, it will generate assertions. If it is simulation, it will generate UVM and start running the tools and even helping debugging the issues. And because it is directly integrated with the Cadence EDA tools, it can run simulation and formal verification seamlessly. When it's done, all the verification artifacts like test plan, test bench, coverage model, reports, and everything is dumped at the end. And DB engineers can take this one and go to the next step and just run the flow by themselves. So this means that like DB engineers can delegate these really like complex workflows, but the key is that they still have full visibility and control over the flow. So they can see all the steps and see how it's going on. The core technical innovation that makes this possible is what we call a mental model. So what is mental model? Um, the mental model is core innovation behind ChipStack. It serves as a structured representation of the design. Mental model captures like design hierarchy, interfaces, functionality of the design, and relationships. This mental model can enable AI agents to reason about the design in a more reliable and consistent way. So, one of the issues with LLM is that they are not deterministic, but this mental model will make it more reliable and consistent. Um, Mental model acts as a shared source of truth across all the agents, and this allows agents to generate correct verification collaterals and make informed decisions. Without this structural understanding, reliable agent-based automation would not be possible. So this is a critical foundation for scaling AI-driven verification approaches. The mental model and agent framework that we have developed are supported by a scalable architecture, and this is our architecture. So as I said, DB engineers or designers can interact with our tool using like VS Code or even terminal interfaces. They can give like natural language instructions. Our agent orchestration, we call it Symphony. They can take their instruction and start using a specialized agents to do the task. All the LLM queries are routed through our backend server, which we call it Jedi. And over there, we have provided telemetry to track the user activities. We have authentication, and we also implemented very strong RAG system and vector database so that we can keep the information about the spec and all the chip design artifacts. Our backend is also flexible. It can connect to any LLM provider like OpenAI, Gemini, and Anthropic models. Plus, we have a fine-tuned model. We call it Chipmunk, and I will provide more information on that. So for customers who are not comfortable to connect to cloud LLMs, they can just connect to our local model, and we use that model for reasoning. So now let's talk about the model layer. This is where it's getting really interesting from an AI research perspective. A core belief we operate from is that frontier LLMs are not at maximum capacity for chip design tests. So these models are trained on general code and text, but as you can see, chip design has very specific syntax, very specific workflows, and very specific correctness metrics. There is a significant gap between what a base model can do and what a well fine-tuned model can do. This table shows three concrete examples that we have explored. The first one is test plan generation. So one of the tasks we have is that the agent will read all your specs, RTL, whatever artifacts you have about your design, and we generate test plan out of that before we go and generate code. So as you can see, by just flow engineering, we could improve F1 from 0.39 to 0.64. So this is just flow engineering. We are not doing any fine tuning. Another example is SVA generation for formal verification. This is also very a specific area, and LLMs are not good in that. In this case, we use SFT, and we could improve llama from 16% to 92%. Another application is VIP instantiation. So when you are doing verification, you also need to use verification IPs. And that's another example that we tried. And for that, we used reinforcement fine-tuning, RFT, which was able to improve the results from 53% to 65%. So basically, as you can see, we have used a hierarchy of approaches to improve our results, flow engineering, SFT, and RFT. And we have done all these three, and I will provide more details for each case in future slides. Let's start with supervised fine-tuning and Chipmunk. So Chipmunk is the fine-tune model that we have. So the task that we selected for this case was to generate valid SVA assertions from natural language test scenarios. So this is a formal verification task. The assertions that we generate, first of all, they have to compile and make logical sense. And when you are verifying a design formal verification, basically you convert all of your test plan, which is in natural language, to SVA properties. So it could be assertions, it could be like assumptions for input constraints, or it could be like cover properties for interesting scenarios in your design. Base models, we realize that they are not good at this because SVA is a niche language and the training data distribution is tiny relative to Python, JavaScript, and other software languages. So the approach we decided to take here to improve the results was SFT. And what we did was that we generated about 24,000 training examples using GPT running our chip stack flow. So first we run our chip stack flow to generate all of this, and then we use some heuristic filters to remove low quality examples. We also used Jasper and EDA tools to make sure we can remove some of the unrealistic examples. Then we did fine tuning on Llama 3. The results we got from here was very interesting. So base Llama gives like 16% assertion validity. That means that 16% of the assertion that Llama can generate, they can compile in, for example, Jasper tool, and they also like logically correct. With some flow engineering, we could get to 64%, but still is far from perfect. So that's why we started to do fine tuning. And with fine tuning, the results is 92%. So that's a big jump, and it can beat the model that generated the training data. So this result that we got from here matters for a few reasons. So first of all, what we have seen is that smaller fine-tuned models can exceed larger general models on domain-specific tasks. In this case, SVA is a very niche language, as I said, and it's domain-specific. So we saw that our fine-tuned model can get better results than the general frontier model. The second fact is that task-specific SFT is complementary to prompt engineering and not a replacement. So as you can see in our examples, flow engineering got you like from 16% to 65%, and fine-tuning was able to get you from 65% to 92%. So these two approaches are complementary to each other. Another fact for us was that for on-prem deployment, a fine-tuned open source model is often the only option because some of the customers won't send their RTL on external APIs. They are not comfortable to connect to cloud LLMs. Definitely the mindset is changing, and we see from time to time that some of the customers were not comfortable to do that, but now they are fine to connect to frontier cloud models. But still, there are some customers that are not comfortable, and Chipmunk was designed with that constraint in mind. Now let's talk about reinforcement fine-tuning, which is a fundamentally different approach. So the task we took here was VIP matching and instantiation. So just to give you a little bit background, when you are setting up a verification test bench, you have verification IPs, and you need to wire your design to verification IP components. a VIP or verification IP has many signals and configuration parameters, and you need to correctly map those signals to your design ports based on the design's like interface characteristics. So what you do is that first need to find like the right set of VIPs that are matched with your design. After that, you need to go and connect all the signals from VIP to your design ports. And finally, you need to configure VIPs correctly based on your design features so that the VIP can just work. This is very time-consuming task and requires like deep understanding of both the DUT and VIP interface spec. And it's exactly the kind of precise structured reasoning task where without a reasoning model might be able to do a perfect job here. So for this RFT task, what we did was that for the training data, we got about 50 annotated samples from our chip design team. So our chip design team basically went ahead and generated 50 samples for us that shows how, for example, VIP is connected to the design interface and how the interface, the VIP is configured. Also for evaluation, we used about 10 samples. And the reward model here was very simple. So we're just doing string matching against like annotated labels. So we didn't use complicated reward shaping here. For this experiment, we ran OpenAI's RFT platform, which gives us access to tune O1 mini and O3 mini. And the runs took about like 4 to 5 hours to finish. So here are the results from this RFT fine-tuning for VIP matching. We got approximately like 12% improvement on top of O1 mini and O3 mini. So these are like frontier reasoning models. So already quite good at the structure task. And as you can see, we were able to move the needle meaningfully with like only 50 training examples. For a highly like a specialized chip design task, like in this case, VIP matching and instantiation, something that is not well represented in general pre-training data, this is a real result. So the broader point is that RFT gives us a way to improve models on verifiable tasks without massive annotation budget. And VIP matching has a clean verifiable reward in this case because you can check whether the wiring is correct structurally or not. So that was just one shot RFT problem. Now we are expanding RFT effort in 3 dimensions. So first one is task complexity. So as I said, the VIP matching was just singleton. The model produces one output and we just go and grade it. But real verification workflows are multi-step. They are tool augmented and require like recovering from failures. So in this step, we wanted to train the model on tasks that match our actual production setup. Second improvement we wanted to do here was about the verifiable rewards. So instead of human label data, in this case, we are using EDA tools as the reward signal. So we wanted to replace human with EDA so that we can generate more samples and in a faster way. So in this case, like what we consider is that if Jasper accepts the test bench and it can pass, then a positive reward is given to the model. If the test bench is failing in Jasper, so the failure message is the signal, and this is fundamentally like a scalable approach. The EDA tool in this case is the teacher, and they can give rewards to the model. And the final difference compared to the one-shot fine-tuning was agentic RFT. So for this example, training is not just the model's response, but it's like tool usage behavior across multiple steps. So we wanted to see if the model can learn how to step by step call different tools to get the final result. So this is the direction that connects like fine-tuning to actual agent improvement. So let me go deeper on the agentic RFT experiment specifically. As I said, the task we wanted to improve here is given a failing formal verification test bench and the Jasper log file, we wanted to train a model to fix the test bench. So this is a real problem that formal verification engineers face like every day. You write an assertion, you run Jasper on it, and Jasper is failing. You have to debug what's wrong. Is it like the assertion syntactically incorrect? Does it like misunderstand the protocol? Is there a port naming error? So all of these errors. The model needs to like read the EDA output, like log file. They need to reason about the design and the errors. And at the end, they produce a correct test bench so that it can pass in Jasper. For this experiment, we collected like 70 test bench from 10 designs. And for validation, we also used 24 test benches across 3 designs. The model has access to the tool. So the model knows how to run the tool. So they run it, the test bench will fail. The model can read the design file. They can also inspect RTL. They can look up the documentation for the design. So all of them are available to the agent. And also the model will receive the Jasper log file as context and extract the error from there. So as you can see, the infrastructure for this task is not trivial. So we are running this on OpenAI Agentic RFD platform again. In this case, we are using GPT-5 and O4 Mini. What we maintain on our side is tool execution server. So RTL and testbench is at our side, and a reward server that can run actual Jasper job to compute the reward is also at our server, and the reward is given to the platform. So the training loop here is that model makes a tool call, which is Jasper in this case. The tool executes against our real EDA infrastructure. Results come back from the log file. The model can take that and they can produce a new test bench, corrected test bench. We go back and run Jasper on the new test bench, and then the pass rate is the reward to the model. So this is, as you can see, this is as close to the production as you can get in a training setup. So this fine-tuning experiment that I just explained is still in progress. So far, what we have seen is that reward can increase over training, but the validation curve is noisy, as you can see. We are working on improving and understanding the results by increasing exploration. But what we have seen so far is that while RFD for a single shot task like VIP instantiation and matching was able to give very good results with only 50 samples, for the tasks that are multi-turn and tool calling is required, we have not seen good results so far, and we are exploring why this is happening. But so far, the result has shown that again, for single shot tasks like VIP matching, 50 sample was able to get good results, but here with more data, we still are not seeing good results. So let me consolidate the SFT learning before we move to the inside slide. What we have seen is that SFT can work. So task-specific fine-tuning can enable capabilities that flow engineering alone cannot unlock for you. And we have seen that smaller fine-tuned open source models can outperform large models on domain-specific tasks. A few practical lessons we learned from this experiment. So first of all, synthetic data generated by the production pipeline is a viable solution. So you don't need like human annotations because that's not scalable. But you do need like human for validation. So that's definitely is needed. The second lesson is that you could just use parameter efficient techniques like LoRa for faster iteration. We don't need like full fine tuning because it's expensive and sometimes it's not necessary. And also, what we have learned is that as you collect like real world production data from customer deployments, so that could be your most valuable future training signals. And we realized that we should not throw it away and we should use it to improve the results. And here is the framework we have developed for thinking about fine-tuning strategy in general. Um, in our experience, it is always better to start with prompt engineering and flow engineering. So that's what we have done for all the verification tasks that we solved so far. If prompt engineering is not enough, we recommend to first try SFT with synthetic data. And if you have a verifiable reward signal similar to what we have from EDA tools, RFT is often more efficient than SFT because you can work with much smaller data set. And the most important like structural insight about verification and chip design in general is that EDA tools are a very useful resource for both rewards and data generation. For example, for verification, we have Jasper, we have Excellium that you can run your test bench and tell you if the test bench is passing or not. We have coverage tools that can give you how much coverage you are getting from your test bench. All of these are like producing a structured, verifiable output that model can use. So what we realize is that we should be mining this aggressively. In RFT, we could use them as rewards. In SFT, we can use them to generate and filter training data. And for annotation, also we realize that we need to leverage internal domain experts rather than like general purpose laborers. That doesn't work here because chip design is a niche area. And people who don't understand the domain cannot generate like valuable data. The third major technical area I want to cover in this presentation is evaluation. How do you know your agent are actually getting better and generating good results? So let me walk through our KPI nightly evaluation framework. The core design here is that every night, a cron job runs our Symfony agent, and we have 15 like different RTL designs, and we run each one like 3 times. So we run about 45 total runs, and we run multiple runs because LLMs are not consistent. So we want to make sure that the results we are getting is like reliable. The metrics we track fall into 3 categories. So first is verification quality. So we use like traditional verification metrics for that, which is pass rate of the test bench. We use coverage values, and we also use correctness of assertions and test benches. Another metric is agent performance, which we consider like latency of the agent, how much token agent is using, and mental model quality. So the results are aggregated per design and per run and overall with mean and standard deviation. And all of them are pushed to GCS, and we visualize them in a dashboard that can auto refresh every night. The pipeline is fully automated and version control. So you can just go back and connect a regression to the exact commit that was causing that. We're also using like Phoenix for local debugging, and OpenAI also has this native tracing for production that we are using to see what agent is doing. So as you can see, like we are tracking all of these, and every night we are going over this and making sure that our results are getting better. And for verification agents, we realize that this is not optional infrastructure. Without this, we cannot ship our product to customers. Um, this slide shows some actual numbers from one of our KPI runs. I don't want to go to details of the numbers, but as you can see, we are getting very good pass rate and coverage values from different LLMs. Even if we enable low reasoning features, you still can get very good results. Okay, let me close with what we learned so far and what is the future for AI verification and chip design in general. So there are three things that made this one very hard and I didn't fully appreciate before we built it. So first one was confidential data. So as you know, like chip companies won't share RTL externally. That means that there is no public benchmark. We have very limited like community data, and you have to build your own evaluation infrastructure from scratch. Everything I have described so far in the evaluation section exists because there was no alternative available. So this is different than Python, C++, and other software languages. So that's one thing. The second one is that EDA tools are very slow and expensive and stateful. For example, if you want to run Jasper on a typical design to finish formal verification, it can take even a day to finish. A simulation with like a good coverage can take like few hours to finish. Your agents cannot run 100 experiments. Every iteration has real cost and takes a lot of time. So this forces you to be like much more careful about when you need to call the agents and when you need to just use reasoning instead of calling agents and just go based on that. Another important problem here with respect to the LLM, and I think this is a general problem, is determinism versus flexibility. As you can see, verification is a formal domain. So there is a ground truth. You need to make sure that you can reproduce the results. You need to go back and run, for example, our agent, and you need to make sure that agent can just take the same, generate the same test plan, same test bench, so that you can reproduce the results. But as you know, LLMs are not like that. So managing that tension between like determinism and flexibility, so that was another challenge we had. And we wanted to ensure that, again, result can be reproduced, but at the same time, we also wanted to have the flexibility so that the agents are more useful. So this is an like ongoing engineering challenge that we are still dealing with. So what I do differently in future is that, so for this kind of application, first we need to invest earlier in real world data, which is captured from like production deployments. And now that we are at Cadence, we definitely have very valuable data that I'm excited to use and improve the quality of our results. We need to invest in a more like robust agent memory system. So this is long-term context across like session and like different users in one organization. And also like EDA tool integration. So that's another very good asset that we have in chip design. So there are many EDA tools that they can give you like feedback about the results you are generating. And the closer the agent is to the actual tool feedback loop, the better it performs. So if you teach the agent to use EDA tools in every step and make sure that the feedback is given and the results are improving based on this feedback, so for sure you can get better results at the end. And the future vision on AI for chip design. So I can imagine a future when there is a design agent, there is a verification agent, and physical design agent, and they can take their architecture spec at high level, and they can work together hand in hand and start from the architecture spec and go all the way to dumping GDS and finish the entire task. So I feel this is future. I'm not sure when this will happen, but definitely the pace of like quality improvement on LLM and all the other technologies coming, I feel that it will happen in like less than 5 years. Okay, thank you very much. I'm happy to take any questions if you have any questions.
Great. Thank you, Dr. Shojay. Great talk.
Sure.
We have a few questions here. William Tang has asked a number of questions. Maybe, Bill, if you can take the mic and ask, that would be good.
Hey, can you hear me?
Yes.
Hey, Hamid, I'm your old office mate, if you remember me.
Oh yeah, William. Yes.
Yeah,
And
nice talking and congratulations on your chip stack development. So
thanks,
yeah,
William.
I have some question about the thing you just talked about. You said the two ticks the spec as the input. So my problem is that the spec is often not perfect. You need to run through the iteration and get the feedback. So is there any the tool is capable to call out the spec that is not making sense and any oversight before we actually go into this iteration to discover the unknown there? Is there
Yeah,
capability?
a very good question. Completely I agree. I've been in also this chip design industry for over 15 years. In fact, actually, I started my career with William, so that's very good to see at Qualcomm. So yeah, in my experience also, usually we don't have a good spec in chip design community. What we did is that, so we did the spec and try to understand what is this spec, what is this design. And if our agent sees that there are some missing information or some information is not very clear, we also go back to RTL and try to understand like how RTL is implementing this. So some of the features that are missing from spec, we try to get them from RTL. But there is a risk over there that if RTL has an issue and a bug, you might get biased towards that bug. So that's why what we generate mental model I was showing. A mental model could be the source of truth. And so again, we read the spec, we read RTL, we understand the entire design, and then we show this structured representation as a mental model to the user. And we ask them, okay, this is what we understand from your design. And we ask them to review that and make sure that this understanding is correct. And if there is anything wrong or missing, we ask them to add that before we move on to the next step. And we made it very easy for the user to give feedback. They can manually update the mental model, or they can even give high-level instruction, and we update our understanding before we continue. And if user is happy with about mental model, then that will be the source of truth. Um, Also, when we run testbench and we see something is failing, we go back again to the mental model and we give warning to the user, say maybe your mental model is not correct, and you need to update it. Another thing that we do is that when we read RTL and spec, if we see that there are inconsistencies between RTL and spec, we also report that to the user and ask them to fix it. So we do all of these, and we're hoping that with this mental model can represent the actual intent of the design. But I completely understand that if human does not want to review, there is always a risk that we don't have the right information over there.
Okay,
Does it make
thanks. Will the generation of mental model pause and ask you the question before it proceed, or you
sense?
will go ahead generate anyways? Because my problem with the LLM is that it doesn't stop to ask me question. It just take what's the most probable course and generate the stuff that could be like a avoid if it can stop and pause and ask me the question. Does that this phone have that capability before it can proceed? Like I don't want to push the button like wait 10 minutes and something is wrong, then I go fix it. I want him to think about it, like for example, just 1 minute. Get back to me with question before you go ahead with all the wrong assumption again.
Completely agree. As I said, the principle we have here is that the user should be on the driving seat and review every step before we continue. I made it exactly like what you just said. After mental model generation, we show that the user in a very nice graphical view, and user can review that and give us green light before we continue to the next step. As I said, we also provided very nice features for the user to give feedback to update the mental model. They don't need to go and update like every section. They can just give very high level instruction and our agent can update it. So yeah, to answer your question, so definitely we generate mental model, we wait for the user to review that, and then we can go to next step. But if user doesn't want to do that, like for a small design, maybe you have a good spec, you don't want to do that, we also have an option that we can go to the end.
I see. Okay.
Thank you, Bill, for the question. There is a related question as well from an anonymous attendee, and that is also regarding if you can detail about the mental model as opposed to the RAG. And he says there was a chart that showed an improvement over RAG that the mental model provides. What drives the improvement in results?
Yeah, that's a good question. So yeah, we did one experiment with and without mental model. So in the first experiment, we just used RAG to extract all the information about the design. And based on that, we went and generated test bench and test plan. In that case, we got like 42% accuracy on the test that we could generate. The second experiment was, in addition to RAG, we first generated mental model. And mental model, as I said, this is a structured representation of the design, which will show you all the important information that we need to verify your design. So, for example, just basic examples like what is clock, what is reset, how many clocks in your design, what are like ports in different domains, different functionalities of your design, and so on. So we extract all of those and represent as a structure format. And then we use that and we realize that using this mental model, we could get 85% accuracy. So it's a big jump compared to just using RAG. And the nice thing about mental model is that we are using a combination of static approaches, like we parse your design using standard parsers and extract a lot of static information. And on top of that, then we go to LLM and combining this static approach, which is like zero hallucination with LLM, then it can give you much better results. So that's why the results could get much better.
Thank you. There's a question from Shahram, and he is alluding to a specific slide number 10. What is the education or expertise level required from an engineer to do this? High school. I mean, so when the LLMs are all doing the job. And I have a related question. What amount of experience for the verification engineer is required to drive this? I mean, is it going to be better if a verification engineer is of higher experience and then the job is going to be much easier, or is that experience required in the LLM, handling the LLM?
So that's a very good question. And so I have seen different cases. So for example, let me give you an example. Like for example, we have gone to some companies that they wanted to always do formal verification, but as you know, there is a like a talent shortage for formal verification. Many companies don't do formal verification, not because they don't know the value, but because they cannot find like PhDs in formal or formal experts to do that for them. So we went to those and we showed them that with our agent, you don't need like much formal verification knowledge. You can just run our tool, and our tool can generate very nice assertions for you. You can even generate the setup and tickle for the formal tool, and it can run it and show you the results. It can even help you to debug the failures and close coverage. So we have seen those cases. But another experience we had is that so the way we are presenting this tool to the community is that this is a like junior formal verification engineer. It's not still like very experienced that can close the loop. That's why I was telling that there should be experienced DB engineer in the loop and review the results step by step so that you can get the best results. So I have seen both cases, but my take is that we actually need more experienced DB engineers for this flow to work, but also this flow can enable like junior people to start like doing verification and gradually learning and closing the loop. So I've seen both cases, but it depends on which stage of the project you are working on. Did I answer your question?
Thank you. Yes, I mean, thank you. Bill has raised his hand once again.
Hey, it's me again. Sorry. So I have a question. So you're using Jasper, for example. So how does the agent understand the failure? Like it can read a VCD file to figure out, like, or it has some special MCP that you're connecting to the Jasper. So yeah.
That's a good question. So before acquisition, we definitely had a parser that could parse VCD and also parse your design and testbench, understand what's going on. Now, yeah, we are switching to MCPs. So we call in MCP tools from Jasper to understand. And Jasper has a lot of nice features that can help you backtrace the failures and understand why this assertion is failing.
Oh, I see. So that MCP is open. Can we just like use it then without the agent, like in general in Jasper, like if we just hook the Gemini up to a Jasper server, we can use that raw directly also? Is that the
Currently, it's
future
not
plan?
open to customers, but actually we are thinking of doing that in future because we have some customers that are asking the same. They don't want to use our head agent, but they want to use our MCP features. We definitely are thinking to do that, but at this point, it's not still available.
I see. Thanks.
Thank you. I mean, I have one more question. So, as you open this machine, is the AI tool at the top level that is going to guide you which tool to be used, or you have to define? The user has to define. Okay, I have an AI tool. Okay, let me also define the tool, and then the tool is being used.
So by default, right now for formal verification, so you are talking about EDA tools, right?
EDA tool. So interfacing with the EDA tool, I mean, does the AI tool go and figure out which interface has to be utilized or which tool in the interface has to be used?
Okay, yeah. So far, like because definitely AI can do that, but it can make mistakes from time to time. But if you use cadence tools, our default is cadence tools, and for example, for formal we use Jasper. For simulation we use Xcelium, and Origin can do much better job over there because we have a lot of customization. But even if you are not using cadence tools, our agent can still support that based on your existing flow. So our agentic approach will figure out how you are running your tools, and it can just run that. So it's not limited to our cadence.
Great. Thank you, Hamid. It's a great talk, and thank you for all your feedback.
Of course. Thank you very much for having me. Thanks, everyone.
Amy? Next week, the presentation is from Dr. Bassam Toussaint from Hewlett Packard Labs. Thank you.